I'm Shravanti, Department of Electrical and Electronics Engineering. So on PSOC, so today our topic is proportional plus integral control. So proportional plus integral control is a device that produces control signal. So that produce control signal which is proportional input error signal. Here the gain increases in accordance with the error signal. So the integral controller is composed of a frequency sensor and an integrator. So the frequency sensor measures the frequency error delta f, and this error signal is fed into the integrator. In fact, the steady change in a frequency will be zero. Steady frequency can be throw back to scheduled value by adjusting a speed changer setting. The system could undergo intolerable dynamic frequency change with the change in a load. So the speed changer setting be adjusted automatically by monitoring a frequency changes. Okay. So without an integral controller, the steady state derivation in a frequency of single area of LFC is delta f of s equal to 1 by b plus 1 by r into delta pc minus delta PD. So for PI control of single area LFC, the black diagram will be 1 by 1 plus STG, 1 plus STT, delta PD, KP by 1 plus STP, delta F of S. Here feedback will be 1 by R, 1 into here integral controller minus KI by S. So even this derivation in a frequency is not desirable. So we have a controller is introduced in the system to change the speed changer setting and make the steady state derivation in a frequency as 0. So delta PC of S equal to minus Ki into integral of delta F into dt. So to apply the Laplace transform, delta PC of S equal to minus Ki by S into delta F of S. So the signal delta PC of S is generated by the integral controller must be opposite sign of delta F of S. So the uncontrolled system is subjected to a steady state error for step load changes. To reduce this error, consider the first the introduction of negative feedback signal from the derivation. Okay, so here 1 by 1 plus st g st 1 plus stt into here delta pd of s will be given output, and we will be given as input, and here delta f of s will be output kp by 1 plus stp. Here feedback will be modified as 1 by r minus ki by s. So and next the transfer function of above black diagram will be delta f of s minus of delta pd of s equal to kp by 1 plus stp 1 plus kp by 1 plus stp into 1 by r plus ki by s by 1 plus stg 1 plus stt. Here delta f of s by minus of delta pd of s equal to kp into 1 plus stg 1 plus st k 1 plus stt, that is derived by 1 plus stp and 1 plus stg and 1 plus stt plus kp into 1 by r plus ki by s. So delta f of s by minus delta pd of s, and simplifying this kp into 1 plus stg 1 plus stt. Here we are taking rs as common, that will be coming to numerator, that is multiplied with rs and divided by here. We are taking as rs will be common. So here s into 1 plus stp 1 plus stg 1 plus stt into r kp into kir plus s. Okay. And next, let us consider a step change in yellow. Delta PD of S equal to delta PD by S. Here delta F of S equal to minus delta PD by S into KP into 1 plus STG 1 plus STT into R into S by S into 1 plus STP 1 plus STG 1 plus STT into R plus KP into KI into R plus S. So using we obtained a steady state value. So by using this equation, we have obtained steady state value. So we are so we have substitute final value theorem, limit s tends to 0, s into delta f of s. So substitute this f delta fss of s equal to limit s tends to 0 minus delta pd by s into kp into 1 plus stg 1 plus stt into r into s by S into 1 plus STP, 1 plus STG, 1 plus STT into R plus KP into KI into R plus S. So delta F of S, delta FSS of S equal to 0. So by using final value theorem, delta FSS of S equal to 0. So from the above expression, the steady state derivation in a frequency becomes 0 with the introduction of integral controller. Okay, so proportional plus integral controller. So the integral controller is composed of a frequency sensor and an integrator. So the frequency sensor measures a frequency error delta F, and this error signal is fed into a integrator. Here this is integrated minus KIYS, and the frequency sensor will be given a feedback, and 1 by 1 plus STG, 1 plus STT into delta PG of S. Here delta PG of S output will be delta F of S, KVS by 1 plus STPS. So the system now modified to PI controller gives to 0 steady state error. So the uncontrolled system is subjected to steady state error. First step load changes to reduce this error. Consider the first introduction of negative feedback signal from the frequency deviation. So delta PC equal to minus K into integral of delta F into dt. So the Laplace transform of above equation gives delta PC of S equal to minus of Ki by S into delta F of S. And first step change of load demand, delta PD of S equal to delta PD by S. So from the black diagram, minus 1 by R into delta F of S minus Ki by S into delta F of S into 1 by 1 plus STG, 1 plus STT equal to delta PG of S. So minus of 1 by R plus Ki by S into 1 by 1 plus STG, 1 plus STT into delta F of S equal to delta PG of S. So delta F of S equal to KPS by 1 plus STPS into delta PG of S minus delta PD of S. So by writing this, minus KPS by 1 plus STPS into delta PD of S plus KPS by 1 plus STP into delta PG of S. So multiplied this, then we get delta F of S. So by substituting delta PG of S from the above equation, we get delta F of S equal to minus KPS by 1 plus STPS into delta PD of S plus KPS by 1 plus STPS 1 by R plus Ki by S into 1 minus 1 by 1 plus STG 1 plus STT into delta F of S 1 plus KPS by 1 plus STPS into 1 by R plus Ki by S into 1 by 1 plus STG 1 plus STT into delta F of S, that equal to minus KPS by 1 plus STPS into delta PD of S. So delta F of S equal to minus KPS by 1 plus STPS by 1 plus KPS by 1 plus STPS into 1 by R plus Ki by S into 1 by 1 plus STG 1 plus STT into delta PD of S. So that implies minus S into KPS into R into 1 plus STG 1 plus STT into S into 1 plus STG 1 plus STPS 1 plus STT into R plus KPS into S into RKI into delta PD by S. Okay. So and next, the steady state value of delta F of t can be obtained by applying final value theorem. So the final value theorem states that delta F of t at steady state equal to limit S tends to 0, S into delta F of S equal to 0. Hence the static or steady state frequency error will be 0 with an integral controller. Next, load frequency and economic dispatch controller. So the economic load dispatch and LFC plays vital role in power system. So in LFC, zero steady state frequency error and fast dynamic response were achieved by a integral controller action. But this control is independent of economic dispatch. So that is no controller over a economic loading of various generating units of a control area. So for a satisfactory operation, using independent control of load frequency and economic load frequency controller provides a fast acting control and regulate the system around an operating point. Okay. So the economic dispatch controller provides a slow acting control which adjusts the speed changer setting every minute in a accordance with a command signal generated by a central economic dispatch computer. So we have to see the diagram for economic dispatch controller and load frequency controller. We have ACE and here integral controller and different integral controller will be send output integral of ACE dt. So that will be speed changes, speed governor, prime mover and alternator. And again we have to take another one speed changer, speed governor, prime mover, alternator. This alternator will send to output to control area of power system. So and if there is any changes, it will send output to the local economic dispatch central. Here PG will be obtained from a central economic dispatch computer. Okay. So and it will send to integral controller and again it will send to speed changer. So this will be continued. So here EDC means economic dispatch control and CEDC means central economic dispatch computer. So the speed changer setting is changed in accordance with the economic dispatch error signal with a suitable modified signal. So that is integral of ACE at that time EDC equal to PG deserved minus PG actual. So the central economic dispatch computer provides the signal PG and the signal is transmitted to the local economic dispatch controller EDC. So the system they operate with economic dispatch errors is only for a very short period of time before it is readily used. So next load frequency control for two area system. So the extended power system can be divided into number of load frequency controller areas. So they are interconnected by a tie lines. Such an operation is called pool operation. When you are taking a two areas connected in a single tie line, so transmission line that connect an area to its neighboring area are called tie lines. The main objectives of LFC is to maintain a frequency of each area or properly regulate the tie line power transferred according to the inter-area arrangement. Here the control object is to regulate the frequency of each area and to simultaneously regulate the power flow through the tie line according to an inter-area power arrangement. Here when you take in a diagram, two control areas are connected to a tie line. Okay. So for the sake of convenience, each control area can be represented by equivalent turbine, generator and governor. Okay. So next mathematical modeling of two area of LFC. So power flow output of control area 1 can be expressed as delta P tie 1 equal to V1 V2 by X12 into sine of delta 1 minus delta 2. Here delta 1 is the load angle for area 1 and load angle for area 2. So differentiating above equation with delta, we get d delta P tie 1 by d delta and V1 V2 by X12 into so differentiation of sine means cos of delta 1 minus delta 2. Here d delta here differentiation of delta P tie 1 equal to V1 V2 by X12 into cos of delta 1 minus delta 2 into d delta. So here delta P tie 1 equal to V1 V2 by X12 into cos of delta 1 minus delta 2 into uh, del delta 1 minus del delta 2. Here del delta 1 and del delta 2 are the change in the power angle. So whenever the change in the load of two areas, then there will be change in the power angle. Here delta P tie 1 per unit equal to V1 V2 by X12 per unit into cos of delta 1 minus delta 2 into del delta 1 minus del delta 2. So by simplifying this above equation, we get delta P tie 1 per unit equal to T12 into del delta 1 minus del delta 2, where T12 is a synchronization power coefficient And next, the incremental change in angle can be expressed in d delta by dt equal to omega equal to 2 pi f. So, integrating both sides, we get delta equal to, so integration differentiation will be cancelled, then delta equal to integration of 2 pi f into dt. So here del delta equal to 2 pi into integration of delta f dt. So change in angle can be expressed as a change in frequency. Okay, so delta p ti1 per unit equal to t1 212 into t12 into 2 pi into integration of delta f1 dt minus integration of delta f2 dt. We are taking as a considering as in equation 1. And next, power transmitted from area 2. So here in the above equation, this is a delta p ti1 per unit. Next, power transferred for area 2 is given as delta p ti2 equal to v1 v2 by x1 x21 into sine of delta 2 minus delta 1. So by differentiating above equation, we get differentiation of delta p ti2 by d delta, and v1 by v2 into sine differentiation will be cos delta 2 minus delta 1. So here differentiation of delta p ti2 equal to v1 v2 by x21 into cos of delta 2 minus delta 1 into d delta. So d delta means change in power angle. So delta p ti2 equal to v1 v2 by x21 into cos of delta 2 minus delta 1 into del delta 2 minus del delta 1. So here delta p ti2 per unit equal to v1 v2 x21 per unit into cos of delta 2 minus delta 1 into del delta 2 minus del delta 1. Here delta p ti2 per unit equal to t21 into del delta 2 minus del delta 1. So t21 equal to v1 v2 by x21 per unit into cos of delta 2 minus delta 1. So p ti2 delta p ti2 per unit equal to t21 into 2 pi into integration of delta f2 into dt minus of delta f1 into dt. We are taking as a equation 2. So dividing equation t21 by equation t12, we get t21 by t12 into pr1 x1 to pr2 x21 into cos of delta 1 minus delta 2 into cos of minus of delta 1 minus delta 2. Here T21 equal to PR1 by PR2 into T12. Okay, so here T21 equal to A12 into T12. This is considered as equation number 3. So taking Laplace transform for equation 1, equation 2, we get delta P T1 of S equal to T12 into 2 pi by S into delta F1 of S minus delta F2 of S. We are taking as equation number 4, and delta P T2 of S equal to T21 into 2 pi by S into delta F2 of S minus delta F1 of S. We are taking as equation number 5. So substitute equation 3 in equation 5. Delta P T2 E of S equal to A1 to 2 1 to 2 pi by S into delta F2 of S minus delta F1 of S, and delta P T2 of S equal to minus A12 into T12 into 2 pi by S into delta F1 of S minus delta F2 of S. That is taking as equation number 6. From a generated load model, power balance equation in area 1 is taken as delta Pg1 minus delta Pd1 equal to 2H1 by F1 of 0 d by dt of delta F1 plus B1 delta F1 plus delta P T1. Here delta Pg1 minus delta Pd1 minus delta P T1 equal to 2H1 by F1 of 0 into d by dt of delta F1 plus B1 delta F1. So taking Laplace transform on both sides, delta Pg1 of S minus delta Pd1 of S minus delta T1 of S equal to 2H1 by F1 of F1 naught S into delta F1 of S plus B1 into delta F1 of S. We get delta F1 of S equal to Pg1 delta Pg1 of S minus delta Pd1 of S minus delta P T1 of S by 2H1 by F1 of F10 of S in plus B1. Here delta F1 of S equal to delta Pg1 of S minus delta Pd1 of S minus delta Pti1 of S by, when we are taking common here B1, then we get 2H1 by F1 naught B1 of S plus 1. So here delta F1 of S equal to delta Pg1 of S minus delta Pd1 of S minus delta Pti1 of S into Kp by 1 plus STP. Here Tp means 2H1 by F1 into B1. So we have drawing a block diagram for above equation. Here delta Pg1 of S delta minus of delta Pti1 minus of delta PD1 equal to Kp by 1 plus STP into delta F1 of S. So from equation 4 we get delta P Ti1 of S equal to T12 into 2 pi by S into delta F1 of S minus delta F2 of S. This is equation number 4. So delta P Ti1 equal to T12 by 2 pi by S into delta F1 of S minus delta F2 of S. So delta P Ti2 equal to minus A12 T12 2 pi by S, delta F1 of S minus delta F2 of S. When you are drawing this black diagram, we get draw black diagram from the above equation. Delta P2 of S equal to minus A12 into T12 into 2 pi by S into delta F1 of S minus delta F1 of S. Here delta P Ti1 of S into T12 by 2 T12 into 2 pi by S into, here delta F1 minus delta F2 of S, here minus A12 into delta P Ti2 of S. Here delta P Ti1 of S equal to minus A12 into delta P Ti2 of S. Okay. So that's it. Next, let us considering the area control area in the presence of the line. In case of isolated control area, yes, ACE is the change in the frequency with when integral controller loop forced the steady state frequency error is 0. So thus, the composite black diagram for two area system can be modeled as shown in figure here. Two area system black diagram, delta PC1, here delta PC2, here minus 1 by R1, here minus 1 by R2 are the feedback. Here 1 by 1 plus STG, 1 plus STT. So and delta PG, delta PD1 and Kp by 1 plus STP and delta F1 of S. Here 2 pi T12 by S and B minus of B12 will be multiplied with this feedback. So here minus 1 by R2 will be feedback. This is a two area system, can be modeled. So this is black diagram for two area system. So that's it. Thank you.